We're going to finish up our exploration of data with tables and graphs by talking about scatterplots, correlation, and regression. So when we have what's called paired sample data, then we can create a thing called a scatterplot, and we can also talk about this idea of correlation or a linear correlation coefficient, which will help us with this discussion of correlation. And we also can do something called linear regression. So we're going to touch on all of those things today. So first off, what is correlation? Well, a correlation exists between two variables when the values of one of the variables is somehow associated with the values of the other variable. All right? Statistics, a lot of times we're really interested in whether this correlation exists or not. More specifically, a linear correlation is when we have these two variables and we have a correlation between them, and when we plot the points of the paired data, we can kind of shove a straight line in there that makes sense and it approximates that data for us. A scatter plot comes into play of giving us the graph of this paired data. So if we have paired quantitative data, then we can use an x and a y-axis to plot that data. So we have one set of quantitative data that'll be shown on the x-axis and one set of quantitative data that'll be shown on the y-axis. And each point is going to be some related pair. So let's look at an example of this. So waist and arm, all right? We're looking at arm circumference and waist circumference. Each point corresponds to a single person. So they took a person, they measure the circumference of that person's waist, and they measure the circumference of that person's arm. And in doing so, they get an XY coordinate that they can plot a point on our scatter plot. Now, if you look at this scatter plot, it looks like there's a line there. It looks, even though it like spreads away from any single line, it looks like it's going from low on the left to high on the right in a fairly linear sense. So in this case, there is a correlation. There's a distinct pattern of the plotted points, which suggests that there's a correlation between waist circumference and arm circumference. And even more than that, it looks like it's going to be a linear correlation. Take, on the other hand, weight and pulse rate. Now, if we look at the scatter plot created here, where we take individuals and we measure their pulse and their weight, and we get the XY coordinates with weight and then pulse, and we plot those, what we have here is kind of a circle of data. There's no real pattern emerging there. Sometimes people call this like a shotgun blast, is what it looks like, where you can't really see any distinct pattern. So that means that there's no correlation between weight and pulse rates. So when we're talking about correlation, we need some tools to help us out. One of the most common tools that you'll see is something called a linear correlation coefficient. And we use the lowercase r for this correlation coefficient. So the linear correlation coefficient measures the strength of the linear relationship or association between two variables. So when we compute this r value, as long as we've done it correctly, it's always going to be between -1 and 1. If it falls outside of that range, we've done something horribly wrong. If r is close to -1 or close to 1, then there's probably a correlation. If it's close to -1, that's a negative correlation. And if it's close to +1, then that's a positive correlation. What I mean by that, with a negative correlation, when one value is large, one variable has a large value, the other one is likely to have a small value. And when the first variable has a small value, then the second variable is likely to have a large value, or vice versa. All right, so for the positive correlation, when one variable has a small value, the other one also has a small value. And when one has a large value, the other one also has a large value. Now, if instead r is close to 0, then there does not appear to be a linear correlation. So let's take a look at an example. Looking at the correlation between shoe print lengths and heights. And the question is there a correlation? Well, looking at this graph, you can kind of see two potential lines that it might fall, and they're very far apart. So looking at this, I don't know where I would put a line through here. It's hard to tell. There's not very many data points, which makes it really hard to tell a lot of times, but it doesn't look likely. But using my whole, is it a shotgun blast or is there a pattern method, it's really hard to tell here. So this is where that correlation coefficient can be really helpful. So if we use software to give us some output and to find that correlation coefficient, the correlation coefficient of that data set is 0.5912691. Well, that's not close to 1. It's not 0. It's not really close to 0 either, but it's not close to 1. But we still look at it and go, well, is it good or not? So this is where this thing called a p-value comes into play. What a p-value tells you is the probability of getting paired sample data with a linear correlation coefficient r that is at least as extreme as the one that's obtained from the paired sample data that we have. So let's look at that value. Looking at that value, the p-value output, which is right underneath of that red box, we see that the p-value is 0.29369, or we could round it to 0.294. 0.294 is pretty high for a p-value. What this is telling us is that there's a 29.4% chance of getting a linear correlation coefficient of 0.591 or more extreme by chance, even if there's no correlation, no linear correlation between our two variables. Well, that's a pretty high likelihood. So we would report this with something like, because the likelihood of getting r equals 0.591 or a more extreme value is so high, there's a 29.4% chance, we conclude there is not sufficient evidence to conclude that there is a linear correlation between shoe print lengths and heights. Now, you might be wondering, what's a good p-value? When would we actually say, yeah, this is good? Small p-values is what we're looking for. P-values of 0.05 or smaller. That's a 5% chance or less that this happens by chance. So if we see a small p-value, then it leads to the conclusion or supports a conclusion that there is a linear combination between the two variables. So let's look at a different data set. Now, instead of only having 5 pieces of data, we're going to have 40. So now looking at our shoe print lengths and height, we can see, looking at our scatter plot, we might say, yes, this looks like there's a relationship here and it looks linear. So again, putting this into software, Minitab is a statistics software, it gives us a Pearson correlation of shoe print length and height of 0.813, which is close to 1, definitely closer to 1 than the 0.5 we had, but we don't want to compare them like that. But again, we go, is that is that close enough to 1 to say that there really is something going on there? And that p-value can help us out. The p-value that we calculate is actually 0.000. It doesn't mean it actually is 0, but it is so close to 0 that we can't find it anything but zeros in those first 3 decimal places. So this is a very small p-value, which means that the probability that this happens just by chance is very, very low. So our p-value of 0.000 is going to support the idea that there is a linear correlation between shoe print lengths and heights. So now, once we've determined if there is a linear relationship or not, if we have this linear correlation or not, once we know that we do have a linear correlation, we a lot of times want to know, well, what is it? How do we represent it? And that's where regression comes into play. So if we're given a collection of paired sample data, the regression line or line of best fit, or least squares line, is the straight line that best fits the scatter plot of the data. This is where you look at the scatter plot and you say that's about where the line goes through, and that is your line of best fit. The regression equation is just the equation of a line, y equals b sub 0 plus b sub 1 x. Well, this is like y equals mx plus b. It's the slope-intercept form of a line, and that just algebraically describes our regression line. So here's our shoe print length and our height, and there's our line of best fit. And again, we can use statistical software to determine what the slope and the y-intercept are. So using that statistics software, we found a y-intercept of 80.9 and a slope of 3.22. So the equation of our regression line is y hat, which is our predicted value of y, is going to be equal to 80.9 plus 3.22 times x. And a lot of times, since y hat and x are variables and they stand for something, to tell people what they stand for, we'll present the regression line equation as actually saying what those things mean in place of them. So y hat stands for the height. It's our predicted height is going to equal 80.9 plus 3.22 times x, which was the shoe print length. So in writing that equation out with what the variables actually mean, then we get that really nice to present equation.